Hello there and welcome back to our small farm. Today I'm going to talk a little bit about two small upgrades I made to my FastCutCNC Elite table, and also one, I don't know at this point, not really important change, So number one, I think this is something I skipped in the previous video where I talked about Mach-free to SimCNC. I'm going to show you how I configured the THC, because I find it wasn't quite the most straightforward process, at least not for me. And then number two, I'm going to show you how I made the table a lot more snappy with some $60 or something of a power supply upgrade. And lastly, I'm going to talk a little bit about some PCB modifications I made. Before we start though, I have one thing to highlight. I'm not an electrical engineer, I'm not a mechanical engineer, I'm a software engineer. In any case, nothing here has to do with software engineering, so this is entertainment only. I don't know what I'm talking about, don't do what I do. Alright, number one. Most simple change, you can see here. This is now 450 watts. Previous power supply was 350 watts. So just a little bit more wattage. So my understanding is that the lead shine drivers in here, they actually top out at 50 VDC. And the only way I could speed up the machine to make it faster would be to use more than 50 volts. So I don't want to replace all the drivers. Because honestly, if I did an upgrade like this, I would just go to Technic servos, and I don't know, maybe in the future I will, you'll see. However, what a little bit more wattage allows me is I can put more amps to the motors, and more amps means they have slightly more torque, which means that I can tune the acceleration in my system. Now, looking at this entire setup here, you can see this here, right? Two linear rails on the top, and this is a helical rack with a pinion. I think this is spring mounted, at least on the sides. You can see that it is spring mounted. There's the spring, which means there shouldn't be any problem with backlash here that accumulates over time. And more torque means that the motors in general can accelerate more without losing step, because they didn't have enough power. The Mach-free configuration that I ported over to SimCNC had an acceleration value of 40 inches per second. And, back of the napkin math and some LLM integrations tell me that with a setup like this, I should be able to go all the way to 80. I've set it up to 80 inches per second, and it seems to accelerate fine. I have a torture test file, which you can see here. And you saw me, I can queue this up and running. And the only purpose of the torture test is to show you if you're missing steps, if you increase acceleration, which is why there are tons of spikes in all directions, so the motor has to stop and start again. And it lands dead on spot where I marked it. I didn't use a gauge or anything to measure it, because I wasn't quite sure how to position the gauge without it getting pushed over by the torch. But anyways, it seems to run great just with the marking. I can see zero differences with pictures before and after. And as an added bonus, I saw that my active phase was wrong. So I fixed that, and now there's no mistake anymore. The power supply unit, it's an amazing upgrade. All right, so for this upgrade, it's super easy to do. It basically takes no effort whatsoever. You literally just take one power supply out. It's two screws on the back, put a new power supply in, screw it back in, and you're done. Like super easy, low risk, can't break anything. Why would you do anything like that? Well, obviously, when you have sharp corners, right, you want to keep the detail, and acceleration in those sharp corners means that your torch dwells for shorter periods of time, which means less to no slack on the back, which just means general cut quality improvements for smaller details, and this is something you definitively want. The machine already is great, right? Don't get me wrong. I'm just trying to get it from a light industrial level to hopefully a much more industrial level, right? So that's number one. Let's talk about number two. So number two is much more involved. You see this here, right? That is a op amp. Technically it's two op amps. And then back here you also have two op amps. And what I did is, I believe those are LM733s, two LM733s, and I replaced those with OPA's 2192. I think for plasma cutting, those op amps are much more desirable because they have much better characteristics, electrical characteristics for plasma cutting. Now, obviously, that brings me to my last point, and that is the torch height control configuration, and we can talk about those things together. Now, for the torch height, what you get is you get a 50:1, that's the factory setting, pre-divided voltage from the plasma cutter, and that is fed into the controller that then makes decisions to move the torch up or down. What stood me up in the beginning is that the 50:1 is not what I have to configure in SimCNC. And the reason for that is quite simply, which I didn't know in the beginning, that the FastCutCNC guys added a voltage amplifier into the board that actually interfaces with the plasma cutter. And then the actual smoothing they have on the board that they mount to the CS Lab IPM. You just have to know about it if you port stuff over like that. So let me cut over to the video so you see how I figured that out. When I originally changed this over to SimCNC, I had big issues with the THC because the machine was always driving the torch into the workpiece. And then in SimCNC, you can configure a multiplier, an arc voltage multiplier. My Hypertherm runs with a 50:1 divider. And when I put 50:1 in SimCNC, it always crashes, right? So with me not knowing better, I just tried around. I set it on 25, 1:25 divider, and that worked. The cuts weren't great. And then I had an idea on how to get the cuts dialed back in. And at this point, I'm basically at the same level as I was before, which is great quality with the FastCutCNC. So here's what I did to reverse engineer the setup. First, I disconnected the cable from the Hypertherm. This is the CPC connector, and port number 5 and 6 are power and ground, or ground and power actually. And then I got my amazingly cheap power supply, which is totally not calibrated. So, you know, this is not the best, but anyways. And then I just took it up. I crimped 2 circular connectors on here, which are from TE Connectivity. So let's get this hooked up again and do some measurements. Because on the one side, the plug I hold in my hand, I know this is a correct 50:1 divider. Right, I totally trust the Hypertherm guys. The machine is expensive enough for that. So it's just what the PCBs in the fast cut control cabinet do. I'm not quite sure about. Right, so makeshift. As you can see, I put a small piece of plastic between to make sure that these don't touch. Then here on the power supply, I have configured it for 0 volts right now and a maximum of 20 milliamps, just enough to make sure that whatever circuit is in there won't blow. Right. Now inside SimCNC, I just go to the diagnostic tab because that's all I really care about anyways. And then on the power supply, I start by powering up and increasing the volts just a little bit. Right. Now we go to 1 volt. We see 1 volt here. And then in SimCNC, you can see 1 volt reads 1.5. Since this is 50-to-1 divider from the plasma, 1 volt would be equivalent to 50 volts on the torch, right? Which means you can already see that there's a multiplier going on. So I think, just from looking at the PCB, that the FastCutCNC folks have actually 2 op amps set up. One is on the control board for the hypertherm machine, and I think this has a gain multiplier of about 1.5. And then the second one on the actual control board that's mounting on the CS Lab IPM, I think it's just a low-pass filter. So anyways, let's go through all the steps from 1 to 10 volts, and then we can see what the value in here actually get. So this is 2 volts. At 3 volts, this is 4 volts. And then 5 volts. 5 would be 250 on the torch. And then 6 volts, it's 8. And at 7 volts, it's also 8. Which means they have a clamp on the board. And I think about a gain of 1.5. All with a simple power supply. Now you might be wondering, why do I care? Well, first I bought 2 PCBs from them. I bought the actual integration with the plasma cutter from them. So I have to know, because otherwise I can't get my rotary plasma cutter to work. And second, I did the conversion to SimCNC with a specific goal of also using SimCNC on my rotary. Now having a plasma cutting table from them means I can basically play around with the real thing, and I know this will work the same way, right? Granted, the actual PCB I use for the integration with all of the things, at this point I think it's pretty much a knockoff of their board, but at least I know everything that's going on in there because I designed it myself. Right, so now that we have this, we can go into SimCNC and configure this. Right, so here we are back in SimCNC, settings, THC, and when you scroll to the bottom, you see there's a torch voltage divider setting, and 33.535 is roughly what I get to, because my measurements aren't exactly 1.5, it's like 1.4 something. But if you look at this, basically it's just say 1 to 50 is what the machine is running, right? And if you divide it by your factor, you get roughly what I put in here. And with that setting, it's actually working pretty good. So why would I show you all of this? Well, both of these op amps are LM7322s, and well, they're great. But me not knowing anything, I actually think I could get the system to work a little bit better by replacing those op amps with a OPA 2192, which I think has much better noise immunity and is actually more sensitive to minor voltage changes. So I think it should be giving me an even better cutting quality. And it's a drop-in replacement. So I'll take those PCBs out, desolder the previous op amps, and solder on different op amps and just see how it goes. And it totally makes sense, right? Again, might mean not an electrical engineer, but if I think about an analog input, right? I basically have 4,096 buckets, right? Which if I map the 0 to 10 volts into, right? Plasma cutting doesn't happen in the bottommost 2 volts. Mostly, at least not, because that's just too low. Don't care about those. And also anything above probably 5 to 6 volts you don't care about, because that would mean that, you know, your voltage is way too high. Usually plasma cutting, I believe, is in the range of, you know, somewhere 80 to 250 volts. If you multiply, right, the voltage you get from the plasma cutter by 1.5, you basically spread out the values so that you can utilize more of those 4,000 something buckets. So the multiplication makes total sense, and it should mean that you get more accuracy in your torch height. The change I made to the OPA 2192 is basically just a more sensitive op amp, right? The more meaningful upgrade that I still have to do is I have to replace their clamping diode, because their current setup actually maxes out at somewhere, it clamps to 8 volts, which means I have 2 volts at the end of the spectrum that I can't use for anything. I found a diode that clamps to 9 point something volts, which means I could actually change the multiplication to something like 2. And this means I would get an even more accurate THC, right? Mind me, I haven't done the last piece yet. I have the resistor to change their voltage multiplier and the diode. I just haven't found the time to replace them on the board yet. I just did the OPA 2192 switch, and that works flawlessly, no issues whatsoever. Anyways, enough technology for today. So far, if you have a fast cut table and you just want to invest a little bit of money and make it a little bit better, get that bigger power supply. It's really hard to mess that up. But also, don't listen to my advice. Thank you.